Today's topic is continuity at a point. Definition of continuity at a point is if a function is continuous at point x equals c, then the limit f of x approaches c is equal to f of c. Simply means the value of the function at the point c and the limit at the point c are both the same. So limit at point c and the value of the function at the point c are equal, then we say the function is continuous. That means there's no gaps, no holes, no jumps in the graph. We can graph the function without picking our pencil from point A to point B. Then we say the function is continuous. So continuity checklist, there's three things we need for continuity. The first one is f of c is defined. That means c is in the domain of f. Limit f of x approaches c exist. And the third thing is the limit and the value of the function at the point c are both equal. For a function to be continuous, it has to be unbroken. That means no holes, no jumps, no gaps. You must be able to draw the graph without picking up your pencil. Here are the examples of functions that are not continuous. So here's first example, f of c is not defined. For that, there's many possible examples. I'm just going to go ahead and graph a function like this where there's a hole at 2. So we have a hole in the graph at point 2. F of 2 is not defined. So this function is not continuous at x equals 2. Next, we have limit x approaches c, f of x does not exist. So that we could have many examples. Here's one that, this is one example, at x equals 0. At x equals 0, I have a vertical asymptote. From one side, I'm going to positive infinity. From the other side, I'm going to negative infinity, and the limit does not exist. The next one, the function value and the limit are not equal. This, again, can be many examples. So I'm just going to draw one that so the function value f of 2 is equal to 5, but the limit x approaches 2 is f of x is equal to 1. So the limit is something different than the value of function at that point. Both of them do not match. Then again, we would say the function is not continuous. So three things we need for continuity. The f of c must exist, and the limit should exist, and the limit and the value of function should be equal at that. It should be equal at the point C. Decide if the given function is continuous and identify its domain. So whenever we're talking about the domain, there's three big things we need to keep in mind. One, if you're dealing with a rational function, denominator should not equal 0. Second, if you're dealing with the radical, then you should not have a negative inside the radical. Inside the even root, no negative is allowed. If you have an odd root, then it's fine. If everything is okay with the odd root, you can use any real number for the input. But for even root, you must have only positive, something greater than 0 or equal to 0 inside an even root. The third restriction is for a logarithmic function, the log of 0 and log of a negative number is not defined. So for your input for the log function should not be 0 or a negative number. Now we have three examples, and we're trying to identify if they're continuous and identify their domain. So let's start by looking at the first one. This function is continuous everywhere other than at x equals 0. Because if x is 0, this function becomes undefined. So domain would be negative infinity to 0. And then 0 to infinity. Notice I'm using the open parentheses around 0. That means 0 is not included in the domain. You cannot have x equals 0. That's not a part of the domain. At x equals 0, we do have a discontinuity. Second, we have a piecewise defined function. Piecewise defined function is that behaves differently in different pieces of its domain. So this function behaves differently when x is less than or equal to 0, and it behaves differently when x is greater than 0. So for this function, let's go ahead and graph this function and see what the domain is going to be. So for x less than or equal to 0, I have x plus 1. So my graph is going to look something like this, and no holes here. There is going to be a closed dot because x is defined at, there is an equal sign here for less than or equal to 0. For the right side, for x greater than 0, my graph looks like Parabola, half of the parabola, x squared plus 1. A parabola shifted 1 unit up for x greater than 0. Now I do have overlapping function at x equals 0 and my hole is covered. I would have had a hole with the second function, but that got covered with the first function. So for this function, domain would be negative infinity to positive infinity. Now we have number 3. Here we are going to look at, first of all, it's a rational function. Before we graph rational function, we always factor and cancel out the common factors. So here we have a hole at x equals 1. At x equals 1, we do have a hole. If you want to find the exact point of the hole, exact coordinates of the hole, plug x equals 1 in the remaining function. So we do have hole at 1 comma 2. If I plug 1 in there, the y value turns out to be 2. And this graph, if I go ahead and graph, it's going to be x plus 1. So start at 1, go up 1 over 1, something like this, with a hole at x equals 1, and that would be a discontinuity. So my domain would be negative infinity to 1 union 1 to infinity. 1 is not a allowed point, or 1 is not in the domain of this function. We can use this idea to extend the definition of continuity on an open interval to the definition of continuity on a closed interval. For a closed interval AB, so we need the function to be continuous in the open interval. We need the left-handed limit x approaches a from the right hand side equal to f of a. Limit x approaches b from the left hand side should be equal to f of b. So graphically, we can say the function is continuous if we don't have holes in the interval a to b, and the function is defined at point a, which is equal to the limit coming from the right hand side. Function is defined at point b, which is equal to the limit coming from the left hand side. And we would say the function is continuous from right and continuous from left at continuous from right at a, continuous from left at b. In the interval, the function will be continuous in the closed interval. The constant function and polynomial functions are always continuous. Constant functions and polynomial functions are always continuous. There's no holes, no gaps, no jumps in the constant functions and in the polynomial functions. The types of discontinuities. Now we're going to discuss the types of discontinuities. There's several kinds of discontinuities. Some are really bad, some are not so bad, some are curable, some are not curable. So let's look at the types of discontinuities. First one, we have removable types of discontinuities. Removable is if limit x approaches c f of x exist and the function value exists, but those two are not equal to each other, then we would say there's a removable discontinuity. Well, limit and the value of the function are not equal to each other. Both exist, but they're not equal to each other. We would say there is a removable discontinuity. Next kind, we have a jump discontinuity. That means limit coming to x from left hand side is not equal to limit coming to x equals c from the right hand side. So limit x approaches c from the left hand side is not equal to limit x approaches c from the right hand side. Then we would say there is a jump discontinuity. Next, we have essential or infinite discontinuity. Either left hand limit or right hand limit or both are equal to positive or negative infinity. Another one is oscillating. Oscillates too much to have a limit. We have seen oscillating function. When your oscillations are getting bigger and bigger, then we would say the limit does not exist if we were coming to x approaching 0 here. Let's see some examples. So which kind of discontinuity do we see over here? We are given a graph. It is not continuous at x equals 2. Why is it not continuous? What kind of discontinuity do we see over here? This is going to be infinite discontinuity. Is it curable? No. The only kind of discontinuity we can cure is removable discontinuity. Next, we have y is equal to g of x squared minus 4 over x minus 2 is not continuous at x equals 2 because the graph has a hole. So this one would be removable because we can redefine the function at 2. Another one, this would be jump discontinuity because we have the left-handed limit and the right-handed limit do not match. So jump discontinuity. Again, this one, the function value is not same as the limit as x approaches 0. So that means we do have removable discontinuity here. Removable discontinuity. The limit and the function value are not equal. Let's look at some graphs here. So go ahead and stop, pause for a minute, try these problems, come back and check with me. okay? Graph f of x is 2/3 x minus 1. X is not equal to 3, okay? I'm going to go ahead and graph here. 2/3 x minus 1. So start from -1, go up 2/3, something like this is how this graph looks like. But there is, x is not equal to 3. So there is going to be hole at x equals 3. That means there is going to be a hole at x equals 3. When x is 3, y will be 1, yeah? So this is the graph, and we have a removable discontinuity here. Next, 2 minus absolute value of x minus 2. So this function, when x is not equal to 2, so it's absolute value of x minus 2, and it's flipped upside down. It's going to be something like this with a hole here, and the value of the function is actually not equal to 2, it is equal to 3. So something like this. This is 0.2, this is x-axis and y-axis. Next, f of x is 4 when x is greater than or equal to 2. It's equal to 3 when x is less than 2. Okay, x is greater than or equal to 2. So this is where 2 is. This is where 4 is. This is where 3 is. So that's what we would have here. And when x is less than 2, the function value is equal to 3. All right, the y equals 3. F of x is equal to 4 when x is greater than 2. F of x is 3 when x is this. This is where the 3 is. Make this line thicker. All right, next we have function with a vertical asymptote at x equals 2. So I do have a vertical asymptote at x equals 2. And we graph this function. This is going to look something like this. All right, so that's going to be infinite discontinuity, and there's no cure for infinite discontinuity. We cannot remove. The only kind of discontinuity we can fix is removable discontinuity. Let's look at some one-sided continuity. A function can be left continuous or right continuous. So coming from the left-hand side of C, if the value of function and the limit are equal, coming from left-hand side, then we say the function is left continuous at C. If coming from the right-hand side of C, the value of limit and the value of function are equal, then we say the f is continuous. F is right continuous at C. Let's look at some examples of left continuous, right continuous, and neither. So here's an example of left continuous. So I'm just going to call this point 2. So that would be, this function would be left continuous at x equals 2. Now we're going to see an example of right continuous. So that would be, again, I'm going to use something similar. When coming to 2 from the right side, this would be right continuous at x equals 2. And then we have neither. So we can have a function which is not left continuous and not right continuous. Again, we can come up with any example. That would be a value of neither, not left, neither continuity at x equals 2. All right, state the value of x in which f of x is discontinuous on the interval -3, 5. Give a reason for each from the continuity list. All right, so here, check out at what points we do have discontinuity. It looks like we have discontinuity at x equals 1. At x equals 1, there's discontinuity. And what kind of discontinuity do we have at x equals 1? Looks like it is removable because the value of function is not equal to the limit. The limit does exist. Limit x approaches 1, f of x is equal to 4, and f of 1 is equal to 5. So those two are not equal, so we would say there's removable discontinuity here. Removable discontinuity at this point. All right, next we have at x equals -1, we have another discontinuity. At x equals -1, what kind of discontinuity do we have? We do have, at x equals -1, looks like we would have a jump discontinuity. Yep, left-handed limit and right-handed limit are not equal, so jump discontinuity. At x equals 3, we have infinite discontinuity. Infinite discontinuity. All right, so that's all the discontinuities in this graph. Note the f is continuous from left at what point? So at what point f is left continuous? Looks like at x equals -1, my function is left continuous because value of function and the limit are equal at -1. Okay, discuss the continuity of this given function. So whenever you're looking at the continuity, it's always helpful to draw the graph and see what's happening to the graph. I need a little more space. Let me clean up a little. X and y-axis, x-axis and y-axis. That's my x-axis and y-axis. For x less than equal to 0, my graph looks like a parabola that is shifted 1 unit up. Okay, so that's going to be a parabola that is shifted 1 unit up. So we have a parabola shifted 1 unit up. Okay, I need a blue pen here. With a covered dot, not an open hole, because I do have equal, less than equal to sign. Between 0 and 2, my graph looks like 2 minus x. It's a straight line, negative x plus 2. 2 minus x is same thing as negative x plus 2. So that means we start, so this is point 1. We start at 2 and go down 1 over 1. So down 1 over 1. And that's how my graph looks like. So when x is 0, the y value would be 2. That's what we have here. And it's going to be a open dot here because we don't have equal sign on the 0 side. When x is 1, y would be 1. When x is 2, y would be 0. Okay, so my graph looks something like this between 0 and 2. Beyond x greater than 2, my graph looks like x minus 2 squared. And that's also going to be a parabola. When x is 2, y will be 0. So I do have a hole covering here. And then when x is 3, y would be 1. So it's going to be a parabola going up like that. Now let's go ahead and look at it. What kind of discontinuities we have at this function? Is this function continuous at x equals 2? At x equals 2, yes. I do have a dot, open dot, but that was covered by a closed dot, so there is continuity at x equals 2. How about continuous at x equals 0? At x equals 0, do I have continuity? No. What kind of discontinuity do I have? I do have a jump discontinuity. Okay, determine where g is continuous for g of x equals x squared minus 4 over x minus 2. Let's go ahead and factor rational functions. You always start by factoring before you graph and cancel the common factors. So we can tell there's a hole at x equals 2 and y equals 4. X equals 2 and y equals 4, we do have a hole. So what's going to be the domain of this function? Domain is the x values. So domain would be negative infinity to 2 union 2 to infinity. Some discontinuities can be removed by redefining the function into a piecewise manner at that point. So here's an example that we just look at. We can redefine this function and make this a continuous function. So how can we make that function a continuous function? Make this function continuous by redefining. So here we see we do have a hole in the given function. We just saw that we did. Okay, we do have a hole here. So my graph looks something like this with a hole at 2. So what we can do is we can redefine this function and say g of x is equal to x squared minus 4 over x minus 2 everywhere other than x equals 2. And this is equal to 2 when x is 2. So when x is 2, this shouldn't be equal to 2, should be equal to 4. The y value should be equal to 4 when x is 2. And now that hole got covered, we redefined the function and it's a continuous function now. Since continuity involves limits, the limit laws or rules all apply to the continuity. Scalar multiple, so if you multiply a continuous function with a scalar, 5, 4, 3, any constant number, the remaining function or the new function will be still continuous. You can add or subtract two continuous functions. Your new function will be still continuous. Product of two continuous functions would be still continuous. Quotient, as long as the bottom function is not 0, the quotient of continuous functions will be also continuous, and composition of continuous functions will be also continuous. Continuity with the roots. So here we're going to talk about continuity with the roots. When are these functions continuous? So earlier we talked about that when you're talking about continuity, should not have a negative or negative number inside the even root. Other than that, everything is okay in the even root. If your even root is sitting in the denominator or odd root is sitting in the denominator, you also don't want it to equal to 0. Okay, so the first one, we want positive only. So 9 minus x squared greater than or equal to 0. That leaves me with 3 plus x, 3 minus x greater than or equal to 0. So my critical values are negative 3 and positive 3. And I'm just going to check. If I plug a 0 in, I get a positive. If I plug a 3 in, beyond 3, if I plug a 4 in here, I get something negative. If I plug a negative 4, I get something negative. So where is this function greater than or equal to 0? Between negative 3 and 3. Is negative 3 and 3 okay? Yes, because that's going to leave me with a 0 in the 0 inside the radical, and 0 inside the radical is fine. Square root of 0 is a real number. It is 0. Next, we have 4th root of x squared minus x squared plus 9. The x squared plus 9 is never going to be negative. X squared plus 9 is always equal, greater than 0. Actually, it cannot even equal to 0. So it's always greater than 0. Because you have added 9 plus whatever x you plug in, when you're going to square it, it's going to become positive. So your domain here would be negative infinity to positive infinity. Next, we have f of x is cube root of x squared minus 2x plus 4. Cube root, there is no need to worry. Any x is okay, because cube root of a positive or negative number is always a real number. So, for example, cube root of negative 64 is still a real number. Square root of negative 64 is going to be 8i, not a real number. So you only have to worry about making sure your output is real when you're dealing with square root, even root. For odd roots, any real number is fine. Polynomials, rational functions, and following are continuous at the points, all points of their domain. So all the trig functions, inverse trig functions, exponential and log functions, they're always continuous in their domains. Okay. There's going to be another video on composition of continuous functions. So if g is continuous at c and f is continuous at g of c, then f of g is continuous at x equals c. See a couple more examples. Decide if these functions are continuous or if there's any point where they're not continuous. So first one we're going to look at, this is composition of continuous function. We have a cosine function and we have inside functions as well. So we want square root of x to be greater than 0. Because it's sitting in the denominator, we don't want it to equal 0. We always want it to equal greater than 0. So that means we want our x to be greater than 0. Anything over x, anything over 0, not including 0, should be okay, should be in the domain. For part B, we have absolute value of x. Absolute value of x is continuous everywhere. Cube root of x is continuous everywhere. The denominator has a little bit of an issue. We don't want x to equal negative 1, because if x is equal to negative 1, we are going to get in trouble. Our function becomes undefined. So negative infinity to negative 1, union negative 1 to infinity. Part C, we have cosecant function. Where is cosecant undefined? Let's think of cosecant 4x is 1 over sine 4x, right? Sine 4x is 0 at multiples of pi. Sine would be 0 at 0 degrees, and then 180, and then all the multiples of pi, positive and negative multiples of pi, sine would become undefined. So whenever 4x is equal to n pi, that's when 4x is equal to 0 when at odd multiples. So we can say x would be n pi over 4. So we have discontinuities at and pi over 4. Multiples of pi over 4. All the multiples of pi over 4, we have discontinuities. Other than that, this function is continuous everywhere. But at the multiples of pi over 4, this function is not continuous. Okay, let's check out the next example. So n pi over 4. So this is going to be multiples of right, so x is n pi over 4. That's all we're left with here. Next, let's look at substitution method to evaluate a limit. If a function is continuous, then by the definition of continuity, limit at x equals c is equal to value of function at that point. So here, let's see if this function is continuous at -3. Yes, it looks like it is. That means I can go ahead and substitute the number -3 for each x in here. -3 squared minus 2 times -3 plus 1. That comes out to be -9 plus 1, which is 8. -8 and 10, that is going to be -1/2. Limit x approaches pi over 4 cosine of x, so that we can simply go ahead and plug pi over 4 for cosine. Because the function is continuous at pi over 4, can we evaluate the following limit using substitution? Let's go ahead and see. Not really, no, because f of x is not continuous at x equals -2. We saw algebraic method. We cannot evaluate this function using this technique. We have seen other methods. We've seen the numerical way or graphical way of evaluating the limits. Next, we're going to talk about limit of a step function. Step function at a split point. What is the step function? Step function's graph looks like this. So it's y equals x with the brackets around. That's called the step function. So this graph or this function would be not continuous at any of the points, because let's go ahead and think about limit x approaches 1 from the left hand side of the step function. When I'm approaching 1 from the left hand side, the limit is equal to 0. When I'm approaching 1 from the right hand side, the limit is equal to 1. So we would say the limit does not exist, and that's the case for any point on this function. So step function is not a continuous function at any of the points. Step function is discontinuous at every single point. In each case, sketch a graph with the given characteristics. So here's the two graphs that I constructed or sketched, but you can use a different graph because there's many infinite possible answers. We want f of 4 to be defined, f of 4 to be undefined, and the limit should be equal to 2. Next, we want f of 3 to be equal to 2 and the limit to does not exist. And that's all for this video. So we talked about continuity here. We talked about left-sided and right-sided continuity.